component? Which target are you going to challenge the recorder?
We challenge you number 11 all elastic band. We can set. Okay.
Hello everyone, I'm a reporter from Team Miracle, and I'm going to present problem 11 boson in elastic band. And here are the problem statement. Connect two metal balls with an elastic band and twist the elastic band and put the balls on the table. The balls will begin to spin in one direction, then in the other. Explain this phenomenon and investigate how the behavior of such a pendulum depends on the relevant parameters. And here comes some important questions. First, which model describes the motion? And second, what are the main parameters? And here is the overview of my presentation. I'll first go through my introduction and then experimental setup and investigation and parameters, then the latest conclusion. And here is the video of this phenomenon. The elastic band which connects two balls is twisted, and then the band will stretch and contract, and the systems will spin back and forth straight up. And we define a period is the time it takes for the balls to change its spinning direction twice, just as shown in the video. And we set up a two-ball pendulum model and define the variables as shown in the following diagram. M is the mass, and R is the radius, I is the inertial or moment of inertia of the balls, and R0 is the original length of the band, and the elongation of it is R. And the angle the ball around the center of the band is phi, and the angle is spin around itself is theta. And the K and kappa's definition is written as shown. And here's our experimental setup. We use different balls in different materials, different size, and different mass, and elastic band and different kinds of surface. And we use tracker and Google Sheets in our experiment. And we connect the elastic band with a lightweight clip. And R0 is measured after the attachment so that it won't cause any error. So first we need to measure the kappa with a torsional pendulum. From this formula, we can get kappa by measuring the period of the pendulum, and we get a constant as shown. And then is our investigation. First, we want to know what is the driving force of this motion, and we believe that it is the restoring torque on the elastic band that drives the system into motion. And we conduct some experiments, find that system doesn't spin when we use low kappa elastic band, and well, it immediately starts to spin when we use elastic band with high kappa. And this ensures our hypothesis. And then we assume that the balls are moving in the manner of pure rolling. And pure rolling gives us the equation that the velocity of the center of the ball is equal to R plus I0 times phi dot, and is equal to capital R times theta dot. And then when the time experience is small, delta phi is equal to d phi, and delta theta is equal to d theta. So we can get the ratio of the delta theta and delta phi, and it's follow the equation as shown. And from the equation, we can come up with some way to ensure our hypothesis that it is moving in a manner of pure rolling. So we consider a half of the cycle. And we can calculate we mark the y out on the ball, and we can calculate the number of times it rotates itself, so that we can get the ratio of delta phi and delta theta. And from this experiment, we found that it's in almost moving pure rolling, and it ensures our hypothesis. And so we need to consider the rolling resistance of it. And it follows the equation as shown, which is similar to the friction. And note that the relation is linear in theta dot. And then we consider whether the damping of the elastic band will influence our experimental result or experiment, and we use a torsional pendulum and measure the maximum kinetic energy of it, and we found that energy decay from elastic band is insignificant. So the rolling resistance dissipates the energy the most, and we can ignore the damping of the elastic band. So then we can write down the rotation equation of the ball, and just as the differential equation has shown. And the solution of theta of t is written as the exponential term times cosine term. And it means that the motion can be modeled with a damped oscillator. So the system will change direction when Seattle change side, and recall that omega d from the differential equation is in this term, so that the period can be theoretical model as 2 pi over omega d, and can be determined by the fundamental characteristic of the band and the surface. And then is the parameters. First, we investigate the period for each cycle, and we found that the period is constant in each cycle, and it can be explained by the theory that it only be determined by the characteristic of the ball and the band and the surface. And the same thing happened when we change the initial angular displacement, and we found that it also stays constant for different theta 0, and it's for the same reason. And then we change the mass of the ball, and we find that the higher the mass is, the larger the period is, and it can be shown in the formula of the period. And we find it's because when the n gets higher, this term gets higher, and making this whole period get higher. So we can. So it meets our zero. It meets our zero. And then we change the surface we use in the experiment, and we found that high roughness and leading to less number of the periods. And when the coefficient of the friction is so big that it's too big, and then the system won't get into motion. So here is our conclusion. First, restoring torque on elastic band drives the system into motion, and then the balls are almost moving in a manner of pure rolling. And then energy decay from elastic band is insignificant, and rolling resistance dissipates the energy the most. And the motion can be modeled with a damped oscillator. And the last, we can theoretically predict our period by the formula as shown. And our main parameters, period stays constant for each cycle, and initial angular displacement theta 0 does no effect on period, and larger mass lead to larger period, and higher roughness lead to less number of periods. And here are our references. Thank you.
Okay, so for the clarifying questions, the first question I'm going to ask is, have you considered the unevenness of the surface? I'm not talking about the friction, it's just the unevenness of the surface. Have you considered that?
No,
Okay, thank you. How about, why don't you talk about the radial linear motion about the system?
yes, okay, let's go to it.
No. Okay, have you considered the radial linear motion here?
We have considered in theory state, but it's too hard for us.
Okay, thank you. Have you considered the length that elongates while twisting?
Sorry.
Have you considered the length of the rubber band when you twist it? Will it lengthen, or is it just stay the same?
No, we didn't consider.
Okay, thank you. Can you go to page 12? page, sorry. Oh yes, how can you why do you think that the constant of rolling resistance is proportional to theta, the first derivative of theta?
Okay, it just has shown that the both on power surface, the rolling resistance is caused by the deformation of the collision, and the more the theta dot is, and it makes larger probability of the collision. So we think it is reasonable that
So do you
it
have a reference or something to support that?
yes.
Okay. How do you? Okay. That's it for my questions. I'll just with the opponents. The opponent from Team Detonation, and I'll be opposing problem number 11, Boson elastic band. So this is the statement of the problem. We think that the focus on this problem should be on which, I think that focus should be which model describes the motion and what are the main parameters. And this is our outline. For the reporter's summary, their theory is that the restoring torque from the elastic band actually is the one that's driving it to move, and they consider the motion of the rolling as pure rolling, and they consider the rolling resistance and the rolling resistance as the main damping from the system. And about the parameters, they test the period for each cycle, and the initial angular displacement, the mass of the balls, and the surface, the friction on the surface of the balls. And their conclusion is that the restored torque from the bed drives the system into motion. And both are moving in a manner of pure rolling. Rolling resistance dissipates the energy the most. Energy decay from the bed is insignificant since the damping constant is small. And the motion can be modeled with a damping oscillator. And for their pros and cons, the pros that they identify the correct key question of the problem. They have a clear demonstration video. They set up model to analyze the phenomenon. And they test out different parameters. But for their cons, they lack the discussion of the kappa value, and the measurements of that is not really clear. And they ignore factors that do not only cause marginal differences. And they lack the clear explanation for the equations. And they lack counter evidence for the conclusions, etc. For example, the pure rolling motion, and etc. And so the discussion, I will be mainly focusing on a few parts. First is the errors from the unevenness of the surface, and the measurement of the rolling resistance constant. And about the theory, I want to talk about the energy decay of the system and the linear motion that they didn't really mention in their report. And now I would like to start my discussions. Okay, first let me continue what I begun before. Can you go back to page 13? Okay, how do you measure the constant?
We didn't measure the rolling resistance.
Okay, so how do you calculate the theoretical time period?
No, we didn't calculate the actual number of the theoretical period.
Then how do you make sure that it fits your theory?
We just
Because I believe in the later PowerPoint of the time period one. The next one. Sorry. Yes, about this. How do you calculate that exactly?
the blue and the red dot is on different surface.
Okay, so that's your measurement problem.
Yes.
Yes, but how do you explain that it fits your theory? Because I don't see a theoretical one.
Just we found that the larger the mass is and the larger the period is. And
Yeah, but that's just the correlation from your equations. Can you prove it that it actually matches?
And just find its relationship above.
But I believe if there's no damping in the system, which means that there will be no B over 2 times I the square of it, isn't that also related to the mass?
The mass is the moment of inertia.
Yeah. Okay. And for the next one, when you're spinning the ball, does the ball always stay on the surface? Yes. Have you considered that it might bounce off the surface if the surface is uneven and causing collisions and errors?
Since we didn't observe that phenomenon, so we think that our surface can be intact.
Okay, let's go back to the theory. So first, can you talk about the radial linear motion? That I really didn't mention how it will affect the system.
Right, so just we have considered for the whole atomic. Here is the AR from the reactant, and we can write the
Okay, so first problem is there damping in the system?
excuse me.
Is there a damping in the radial system?
You mean the
Yeah, the elastic band. Or should that be considered, or is it insignificant?
we think that it's insignificant.
Okay. How do you think that this motion will affect the whole system, or doesn't really affect anything? because you consider the ball as pure rolling, right? So on its tangential side, it should be going this way. But as the video, we see that the ball actually extends and contracts. So shouldn't there be like a sliding friction this way?
Oh yes, and that.
Okay, while you're looking for it, I want to.
We calculate the effect from the radial friction. Yes, we calculate the energy decay from the radial friction, and we found that it's the order of magnitude of it is too small, and that is insignificant.
Okay, but have you calculated the energy decay from the friction, the rolling resistance? From the rolling resistance, because it also takes energy away from the system. Right?
Yes, and
yeah,
the order of magnitude is like 10 times the zero.
So is it smaller than this?
No, not larger than.
Larger is larger than this. Okay. So, but how does? So you mean it's a lot way smaller than this? Can you calculate it for me?
Just.
I mean, how do you calculate the energy decay from the rolling resistance?
This is the torque restoring the rolling resistance constant. This is the energy decay.
Do you have statistics of your calculations, like numbers? Because according to your theory, I believe you think that the main reason for the energy decay is because of the rolling resistance. Is that true?
Yes.
Okay, so the reason why the ball stops spinning is because it's mainly because of the rolling resistance. Do you have numbers too? Exact numbers, like how you calculate the radial friction? Okay, it's fine. If we can measure the the rolling resistance and we compare it with the radial friction, I think we can have a better acknowledgement of how the energy is lost from the system. And why doesn't this part of the energy affect the pendulum of the time period? Why does it not? I mean, why does this friction don't affect the time period? Because inside of your formula, it's only about the rolling resistance, the damping from the rolling resistance.
Yes.
And so why does this friction don't affect?
Period. We calculate from the equation of the rotation equation of the ball.
I understand. But the damping constant is from the rolling resistance. How about the sliding friction?
I mean the radial.
Because okay, I'll skip that. How about the energy that you predicted from this motion? Have you predicted the energy of the system using this, or?
any decay will decay, the amplitude of the energy hopping will decay slowly.
So is that the kinetic energy? Okay, that's the kinetic energy. So does it fit the theory of what you just mentioned? The formula is written, the simplified formula is written as does it fit the energy of this?
Since we want to get the damping ratio B over I, and we need to fit the amplitude decay curve.
Okay,
I think
so
the dot is so too little, just not enough.
Right.
We don't do.
I think this part of the energy maybe needs more investigation, because I can't really tell whether the main energy loss from like these two peaks are from the rolling resistance or the sliding friction. And that, since that affects how many cycles, the total cycles of the system. What do you think? Is it because of the rolling resistance, or is it mainly because of sliding friction?
I still think it's because of rolling resistance.
Okay.
Because it's happening from the B, and which is referred to the rolling resistance.
Well, on my opinion, I think that we can actually approximate the rolling resistance into a simple constant. Since while you're doing this in the system, you actually, well, I assume it as a constant. So if we calculated the rolling resistance, the average value of the rolling resistance is usually like 10 to the power of -3, usually, and at that magnitude. And when you're calculating the rolling, when it's rolling, you if you want to calculate the energy that's lost from the system, you have to calculate the length that it runs, right? So it's about how long, how much does the ball run?
During one.
During, okay, maybe half a cycle.
You mean the time for the distance?
The distance, the ball runs.
It's like the radius of the case is like 5 to 10 centimeters.
Okay, but I still really don't understand why when the ball is extending and contracting. Okay, I'm sorry. During the discussion, we talked about mainly the point they didn't talk about the radial lengths and how they measure about the rolling resistance. They didn't really give a clear demonstration of how they calculate the rolling resistance and how it affects the system. And I don't see a fitting about their theoretical time period and their measurements. So I think that could be one of the improvements. I think indeed the motion of the linear one is actually complicated and maybe not solvable. But I still think that the energy loss throughout the system should be considered inside your calculations. And about the cycles that we talked about, I think there should be more investigation in it about how the energy loss and why the cycles are smaller. Thank you.
So my first question to both of the reporter and opponent is, did you guys consider the chaotic unstable buckling effect, where if you have enough turn of the rubber, it sometimes buckle rather than just straight? So did you consider about that phenomenon or no? No. What do you think about?
I think it do affect, but according to their theory, they only talk about the spinning and motion.
My next question is, how do you guys think what type of friction are in the radial direction and then the theta head direction based on your presentation? So reporter, can you speak about this idea? What kind of friction force are they in radial direction and theta?
Kinetic friction.
Sorry?
Kinetic friction.
So you think both of the radial and then theta head direction is kinetic friction? Okay. How about you?
I believe on the radial side it's kinetic friction or sliding friction, and on the radial side it's the rolling resistance. The tangential.
Yeah. Okay.
Sorry.
My next question is, did you consider different rubber band? No. What do you think about how different rubber band will affect the overall?
According to their presentation, they mentioned about the first few pages. They mentioned how the kappa value affects.
Okay, thank you.
So we didn't come by it.
Okay, thank you. My next question is, how does the spring force of the rubber band contribute to the radial direction of the force? So could you explain how would it affect the spring force of the rubber band will influence to the overall radial direction? If you don't know, it's fine. How about your take?
You mean how the radial is
Radial
affected?
direction of the spring force that rubber band itself gives it to when it expanded or shrinking down.
I believe while it's twisting, the rubber band actually lengthens,
Yes.
so that needs to be one part of the consideration.
Okay.
And another part is that the time period, we can actually approximate the time period of the rubber band extending and contracting, because since it should be the half of
Okay,
this one
that's good.
cycle.
Thank you. Did you consider the threshold for the friction coefficient that lead to getting to the static friction, or did you consider not at all? Because that will matter for maybe testing different floor, because each floor has different coefficient.
Can you refresh?
So did you consider the threshold of the friction coefficient that will lead to the rolling without slipping, or whether it's just slipping? Did you consider the threshold coefficients? If you don't answer, it's fine. What do you think about how does the threshold coefficient will affect the overall shape?
You mean the coefficient?
Yeah, for example, some slippery floor versus really rough. Yeah,
I believe the coefficient of mainly on rolling resistance actually affect the time period and not the sliding one.
Okay, thank you. How do you think about the temperature change of the rubber band will influence your overall phenomenon?
I think like temperature goes up and you're easy to stretch.
Okay, what do you think
I think
about?
mainly from their measurement of the damping constant, we can see that the damping of the rubber band actually significantly small, so it could be ignored.
Can you talk about that? Thank you. Hello everyone, I'm Hyun Chun from the All Nighter, and today I'm going to review about the discussion between the reporter and the opponent. So what I think for the main focus are why the balls spin in such manner, and how do the relevant variables affect the angular and radial acceleration and the stability of such system, and then what are the special phenomena observed in the system. So reporter did a pretty good job overall, like good introduction, simple video model with the video demonstration, and then they also talk about restoring force that influences elastic bands, causing the spin of some pure rolling, dampening, and then period. However, there's an issue for the time issue, and then they assume elastic band is ideal spring, and then the parameter test very limited. They only have 2 methods tested, and there's no comparison between the theory and the experiment, and then there's also lack of error bar. For the opponent, he did also a pretty good job. He talked about the surface unevenness, length of the band, or radial friction. Pro did a good job for asking about the theory and calculation. There will be lack of information or explanation. However, they have some cons, like some questions are unclear and it sometimes does not express own opinion, or the time management also has some problem. So the opponent talked about the consideration of the surface unevenness, and then the reporter said didn't observe. However, it's possible that it will disrupt the harmonic motion, angular velocity to reach the equilibrium, and also the angle passed after the equilibrium. So bomb can also shift the center of the mass. So the reporter cannot assume that the center of the mass is fixed. So next slide. So they talked about the radial friction. So opponent talks about they're missing sliding friction in the radial direction, and then the reporter said they calculated the effect of the radial friction, and it is too small, so they neglect it. However, it is significant. Due to the spring force of the rubber, it gives you the external force, and it will start to slide the ball. So rather, it will have the kinetic friction energy rather than the static friction energy in the radial direction. They also talk about energy decay, rolling, resistance, and bend motion. And here's some pointness. So they never talked about the chaotic unstable buckling effect. However, it can buckle and make the natural wedges smaller, and it can also influence the angular velocity. They did not consider anything about the temperature makes the strength weaker. This is crucial because it could be one of the parameters they could have tested. And then they also talk about different type of friction in radial and data head direction. Because spring force gives the ball strength, so it will rather sliding than static, just rolling without friction. So they did not talk about overall velocity vector. They only analyzing the data head direction and the radial direction, but they did not talk about the vector sum of the radial and the data head direction. And then they did not consider about they only consider about torsion of the rubber, torsion constant of the rubber band. But then each band has a unique torsion and also spring constant. So by changing the different type of the rubber band with the thickness, give you different type of the force or different type of the revolution period and angular velocity. And they lack of explanation why it moves in under that harmonic motion. It could be due to the radial kinetic friction from the spring force. They lack of explanation of stability of the system, and they also lack of empirical calculation of the threshold coefficient of the friction coefficient to make the ball kinetic or static motion. They lack of analysis, like their lack of error bar, so we cannot tell whether they only test one time or multiple times to get to the results. And then they also lack of force analysis of both radial and the data direction. We believe there should be more consideration of the friction force and tension and also other spring force. So that's all my video presentation. Thank you for listening.
Here's the concluding remark from reporter. And first, the radial motion is very, we think that the radial motion is very small, so we think the influence of it on the period is also small. And we think the effect of blocking of the rubber band is small since it returns to the initial shape very quickly. And third, compared by, we think the effect of temperature on the rubber band is small. And since the temperature stays relatively constant through time, and also we measure the time for the pendulum to turn to its equivalent place and to the particular period, and we found that kappa isn't affected by time, and we think that it also won't affected by the temperature. And the last, our theoretical calculation tells us what parameters should be tested, and we hope to quantitatively analyze the system in the future. And that is.
Questions or three more questions?
Okay, would you please turn to page 20? Yeah, would you please tell me about the period, what's the relationship between the period and the mass and the kappa and the mu k and the c and the radius, because you have so many parameters here, I don't know what are you going to tell us about your theoretical equation and your experiment. So would you please tell me more about your experiment or your theory?
This graph shows that this graph is our equation, and so that I ensure that the higher the mass is, the larger the series, and we can find it in the theory that the mass appears in this term and the mass gets higher. This term will get smaller and closer.
Yeah. But I think this is proportional to the mass.
No, we just.
It's okay. How about opponent reviewers? Opponent first. Could you tell me about it based on his theory? What's the?
I think I agree with what the reporter said, but I don't think it's clear enough to show about the actual relationship between these two.
So what's the curve you think based on this theory?
I think the curve will be going upwards, just like what the reporter said.
A straight line or some?
It cannot be a straight line.
So what's the shape of the curve? It's okay. How about reviewer?
I think it's going to be increasing at the beginning, but then decreasing at the end.
So it's a curve about optimize some optimize situation. It's okay. Thank you.
Question for the reporter. In your video, you show the process of motions. Does the center of mass for the full system moves on the plane?
Yes, it will.
What is the cause of this movement?
And it will cause some error for measuring the part.
What is the reason for the movement? Why it moves? The center of mass, why it moves?
Maybe the friction acts on two bolts are not equal.
Do you want to ask other two? No. And then other question?
Okay. Would you please turn to the page 8? Yeah. Do you think the kappa you measure by this method will fit the motion of the case? Yeah. Is this the same? Yeah.
What possible?
The question is, you measure the kappa, the tension constant here. Is that will be matched with in the real case that two metal is rotating the torsion constant in that case, rubber band.
We don't quantify the effect, but we think from theory about when the kappa goes up, the period will go down.
So how about opponent?
I think it would affect, since kappa is not a constant while your rubber band is lengthening or twisting.
Yeah.
I don't think that's a constant. And another part is that whenever you're spinning a rubber band, it's actually also a damped motion, so maybe that should be taken into consideration.
Yeah. How about review?
The torsion is fine by fixed at one point and then give a twist on the other. But this one is ball being rotating in the other way, so I'm not sure if that's correct representation. It could be have the more torsion constant than what this one is, this theory is doing. So I think this is underestimating the actual torsion constants.
Okay, thank you.
I have a question. Since the rotation is under the condition that two rubber bands have some external force here, right?
Yeah.
But the major torsion is measuring this one. If I somehow put the torsion not take into account that the ball is on the ground, without the measurement, the torsion will be the different.
So, is your question asking if you put the system in vertically rather than horizontally?
Yes.
I'm not having a clear answer for that, but I think it could also refer to the buckling effect, where the gravitational force will not buckle anymore, so it has some strength of the natural radius, stretching the natural radius in vertical direction.
Do you want to answer?
Can I answer? I think the kappa value is actually only related to the material itself, its state, but while it's spinning on the ground, there could be other factor that's affecting its motion, including like the damping from.
Why?
Because the rolling resistance is actually taking.
Why?
Why? About.
The torsion frequency is due to this one. But the spin constant is related to this one.
Yes.
The motion.
I mean, why does the motion spin?
Yes.
Why
Why the motion of that one will affect on that one?
I don't really think that the radial one will affect how this spins. It's because that I mainly think this is because while the force, the direction of the force is actually.
Do you want to answer?
I think the last is that concluded. Since we turn it in different angle and it didn't affect kappa, so we think the effect of it is insignificant.
How did you measure the torsion constant during the rotation? How did you measure the torsion constant during the rotation?
We measure the time, the pendulum spin period.
And you measure the condition that for the different length, the torsion has to be the same because you are rotating. The distance between two poles is varying. Okay. Stop.
Well, it's not here.
The jury's question was about whether you can always assume the torsion constant is independent of the length.
Yes.
That's the question. Do you understand the question now?
For the recorder, 66755. Okay, for the opponent, 87866. Okay. For the reviewer,